Welcome to Sweet Spot Maths, the gold standard for A-level maths teaching. I'm David Forster. This lesson is on mechanics revision, and I'm going to use the Edexcel 2020 paper, Mechanics, and I will cover questions 1 to 3 in this lesson. This paper is a good one to use for revision because all 5 questions are fairly standard situations that you should know and understand, with very few awkward parts. So the 3 questions will be: first, a particle resting on an inclined plane and the forces involved; secondly, motion under constant acceleration; and thirdly, motion with variable acceleration. And both of these use vector notation. Question 1. A rough plane is inclined to the horizontal at an angle alpha, where tan of alpha is 3/4. A brick is placed. The brick is in equilibrium and on the point of sliding. Model as a particle. First of all, find, in terms of m and g, the magnitude of the normal reaction of the plane. Now, we're probably going to need a good diagram, and we need to understand the forces that will act on this particle. So there are 3 forces only. There's the weight mg going from the center of the particle vertically downwards. There's the friction, which will be going directly up the plane to prevent movement or oppose movement. And the normal reaction will be at right angles to the plane. The question here says to find n. Now, in these questions, the best way of dealing with this is to resolve perpendicularly to the plane and along the plane. So if we go perpendicularly to the plane, there are 2 forces with components in that direction. N, the normal reaction, and the weight mg has a component normal to the plane and a component along the plane. So we have mg downwards. We want to go to the component perpendicular to the plane. That's going to be mg cos of alpha. Now, we're dealing here with the triangle. We were told that tan of alpha is 3/4. So this is our 3, 4, 5 triangle. Cos of alpha will be 4/5. So n will be mg cos alpha. Mg times 4/5 equals 4/5 mg, which is what we were asked to find. We were told it was equilibrium, which is why n equals mg cos alpha. They cancel out. There's no movement, no resultant force in that direction. Part B, we're asked to show that mu is 3/4. Mu is the coefficient of friction. We're told that the brick is in equilibrium and on the point of sliding, and we're going to use both of those facts to do this question. So this is part B. We're going to resolve along the plane. Along the plane, there are 2 components. There's friction going up the plane, and there's a component of weight down the plane, which will be mg sine alpha. Sine of alpha is 3/5, so friction will be 3/5 mg. We know the normal reaction already. We're told the particle is on the point of sliding, so by the friction law, friction is limiting at its maximum value, F equals mg. Substitute in the values of F and n. M and g cancel, leaving mu equals 3/4, as asked. Part C of the question. We're now told, do not do any further calculations. From now on, it's explanations and descriptions only. So brick P is removed and a much heavier brick is placed on the plane. The coefficient of friction, 3/4, is unchanged, and we're asked to explain briefly, for 1 mark, why brick Q will remain at rest on the plane. Well, the answer to this is that the angle at which a particle slides depends only on the coefficient of friction and not on its mass or weight. So we need a concise 1 mark answer, and I've gone for the forces acting on Q will still be in equilibrium, the F and N values both increasing proportionately. You can see from part B, M and G both cancel out. The mass and the weight don't affect the calculations here. Part D. Brick Q is now projected with speed 0.5 meters per second down a line of greatest slope of the plane. It's a particle. Describe the motion of Q, giving a reason for your answer. Now, previously, Q was on the point of sliding. It wasn't quite sliding, and it was in equilibrium. It started moving. It's still in equilibrium. That means there is no resultant force, and that means by Newton's laws that Q will continue in that constant speed of 0.5 meters per second. So the answer is going to be that Q will slide down the plane with constant speed because there is no resultant force. So for this question, A and B are standard work. Make sure you know really well how to do these questions. They're really very common in mechanics papers. Resolving horizontally and vertically would do as an alternative to going along the plane and at right angles. Any two directions will do. Why are along the plane and at right angles the best ones to take? Well, it's because two of the forces are already in those directions, and we only have to resolve one force, which is the weight. Any other direction, we'd have to do more resolving, more work. Mu equals tan alpha, where alpha is the angle of sliding. This is independent of mass. That's part C. If you want to get an idea of what values of mu are high values and which are low values, we can use this idea that mu equals tan of the angle. So the tan of the angle is 3/4. If we work out the angle from that, that's going to be less than 45 degrees. With a mu of 3/4, this will slide at maybe, shall we say, something like 40 degrees. That gives us an idea of how big the mu value is that we're talking about. Equilibrium, a technical term here in mechanics, means forces cancel out. So by Newton's laws, either the object is at rest, i.e. it's still, or is moving at constant speed. That is part D. And make sure in any explanations or descriptions you use the correct terms, e.g. resolve, equilibrium, etc., not in formal language. So maybe a quick peek at the mark scheme, at the examiner's report, I should say. So overall in this paper, quality was very mixed. Some very good, some less good. A reminder that the numerical value of G should be 9.8 unless otherwise stated. We didn't need it in this first question. And final answers are then given to 2 or 3 significant figures. And going more accurately than that will be penalised. If a candidate is asked to show sufficient details, then make sure that is done. A show that question means correct answers without working may not score at all. Question 1. First part was well done by the majority of candidates who resolved perpendicular to the plane. Occasional confusion between sine and cos. Horizontal resolution is an alternative valid approach, but not so easy. M cancels out. In part D, the majority of candidates failed to realise the brick would continue to move down the plane with constant speed, since there is no resultant force. Most thought it would move with acceleration because of weight or gravity, or with deceleration because of friction. Okay, so let's have a look at question 2 of this paper. A particle P moves with acceleration 4I minus 5J. That's a constant vector. So we're dealing here with constant acceleration. So those equations of constant acceleration, what you might call the Suvat equations or UVAST, can be used here, but using vector notation. We're told the velocity when t is naught. That's the u velocity. and we're asked to find the velocity of p at the time t equals 2. So this question involves v, u, a, and t. The equation we want is that v equals u plus at. We're given the u value, we're given the a value and t, put those in, and we get the velocity being 6I minus 8j meters per second. Strictly speaking, we should be putting in the units because this is a velocity. We're then told that time t is 0, p is passing through the origin. At time t equals big T seconds, the particle p passes through point A. We're given the position vector of A, and we're asked to find the t value. So in this question, we're dealing with displacement, initial speed, acceleration. The equation we want is that s equals ut plus a half at squared. Put in the s, u, and t values and a value. We get this equation here. And this is the point at which some candidates will become stumped. But in fact, we can take components. I and j can be treated independently. And if we take the j component, we get an equation with t in it. It's a quadratic. It has solutions 1.8 and minus 1. Discard minus 1 since t must be positive. Big T is 1.8. Don't really need units because t is just a value. Part C, hence, find the value of lambda. A reminder that hence means use the previous answer. So we're back to this equation in part B. Take the I components. Lambda will equal minus 2 times 1.8 and a half times 4 times 1.8 squared, which is 2.88. Now, this is an equation of constant acceleration. You could have used integration for this. It's not needed. It's probably harder. If you do use integration, then remember the plus c. And as I said earlier, taking components is going to stump some candidates. That's where you need to think like a mathematician. Taking components is a standard thing to do, but you've got to think of it. A quick peek at the mark scheme for question 2. First part, the majority of candidates used the right equation. Some chose to integrate, often successfully, but often forgot the constant. I think that's enough for question 2. Let's have a look at question 3. So question 3 is the case where we have acceleration which is not constant. So we do not use the equations of constant acceleration. A common mistake would be to use those equations where they're not valid. So we're given a in terms of t, and we're asked to find the velocity. We've got to integrate. So velocity is the integral of a dt, t minus 2t squared I, add 3t minus a third t cubed j, plus a constant. When t is 0, v is 36i, so the constant is 36i, and putting that in with the i's, we get a formula for velocity. What are we asked to find? The velocity of p when t is 4. So we put in t is 4, and we get the velocity here. Strictly speaking, we need the units, meters per second. It is the velocity we're asked for, not the speed, so leave it in vector form. Part B, find the value of t at the instant when p is moving in a direction perpendicular to I. Instant just means the time. Moving in a direction perpendicular to I, right, this is something we need to know, is that means that the I component of velocity will be 0. That's something which, if you've not seen it before, might confuse in an exam. So we're going to put the I component of velocity to 0. So we have a quadratic. T is 4.5 or minus 4. Once again, t must be positive, so the time is 4.5 seconds. Part 2. This is once again non-constant acceleration, but part 2 and part 1 are independent of each other. We don't want to start using anything from part 1 in part 2. So at time t seconds, A particle Q is moving, and we're given the displacement, the position vector, is r equals this vector here. And it says find the value of t at the instant when the speed is 5 meters per second. The speed is the modulus of the velocity. So we differentiate to find the velocity. dr dt is 2 t take 1I, add 3j. We want the magnitude of this velocity to be 5. So 2t take 1 squared, add 3 squared equals 5 squared. You'll probably recognize again the triplet 3, 4, 5 here. Second time it's turned up in this paper. So 2 t take 1 squared equals 4 squared, 16. T is 2.5 or minus 1.5. And once again, t is positive, so t must be 2.5 when the speed of q is 5 meters per second. So a quick peek at the mark scheme. Question 3. This involves variable acceleration. A significant minority tried to use the Suvat equations and so had no credit. Quite a common mistake here. Neglecting to include the constant. Once again, quite a common mistake. In part 1, part B, candidates need to realise that moving perpendicular to I implies the I velocity component of V is 0. Worth noting that, worth writing it down. That's something that if you've not seen before, it would be difficult to work out in an exam. Take a note of that. Moving to part 2, generally more accessible. Even those who used Suvat in part 1 now realised they had to differentiate. Most knew how to use the given speed to find an equation in t, but some tried to do silly things like equate the vector to 5. Okay, so in this paper we've looked at 3 standard situations, all of which are worth knowing well because they come up quite often in mechanics papers. So they are a particle resting on an inclined plane and the forces that involves, motion under constant acceleration, the Suvat equations, including using vector notation, and thirdly, motion with variable acceleration, where we have to differentiate or integrate, including here using vector notation. In the next lesson, I will go over questions 4 and 5 from this paper, which once again are standard situations which are worth knowing. This is Sweet Spot Maths. I'm David Forster. Sweet Spot Maths does maths in the sweet spot, fine-tuned to achieve A* without wasting time, which are designed to shift your perspective so you think like a mathematician and complete even the hardest exam questions correctly and with confidence. And thirdly, to learn those exam secrets, the gaps, mistakes, and omissions of other candidates to get the exam edge, the competitive advantage, by making the mistakes of other candidates your areas of strength. If you would like further information about the Sweet Spot Maths course, then do email me on maths@davidforster.org.uk and I'll be delighted to send them over to you. Thank you for taking part in this lesson.